Hello class, this is Learning Plan 8, your last learning plan for water technology. We're on chapter 9 of your textbook. I have the closed captioning on. I just wanted to do a test on this. So hopefully this will help me slow down and then hopefully you can read what I'm saying. Okay, with that. So, estimating storm runoff. What we're going to discuss is the rational method. It's the relationship between peak runoff and rainfall. So Q is the peak rate of runoff. Q is a familiar term you should be aware of, is cubic feet per second or cubic meters per second. That's your flow rate. So we're talking about flow rate instead of in a pipe or a channel. We're talking possibly surface flow. C is a dimensionless runoff coefficient. So if you look at table 9.1 of your textbook here on the upper right hand side, you can see that based on the type of material that water is running over, the runoff coefficient changes. So if you look at a woodland area, runoff coefficient is 0.01 to 0.2 versus like pavements and roofs are 0.7 to 0.95. So basically, the smoother the surface, the longer or the faster the water or more flow will happen. Okay. I is rainfall intensity, and that's in inches per hour and meters or meters per hour. That was discussed in the last learning plan. A is the drainage area basin. Okay, so if you look at the next figure on the right, so when you look at it, a storm discharge. So when it starts raining, basically, let's look at the Fox River system from Lake Winnebago all the way until it gets to the bay. So before that flow is seen at the De Pere Dam, which is the last dam in the system, it takes time for that water that fell in Lake Winnebago to travel down that stream to create a maximum flow, which you see right there. And then the flow will slow down. Okay, so that's something to keep in mind. So Q equals C times intensity times the area. Okay. So let's do example 9.1 from your textbook. And that is on page 218 of your book. Okay. So example 9.1, it says, estimate the peak rate of runoff on a 5-acre watershed. So we have 5 acres watershed from a storm with a rainfall intensity I of 3 inches per hour. So this equals A. I equals 3 inches per hour. Assume that the dimensionless runoff coefficient is 0.4. So C equals 0.4. So write down your givens. Okay, I'm going to change my ink color here. Let's go to black. All right, so using Q equals C times I times A. So we have 0.4 times 3 times 5. So if I multiply this out, I get a flow rate of 6 cubic feet per second. Okay, which is not a lot. So let's look at the units here. So in the English units here, Q is cubic feet per second. Okay. C is dimensionless, so there's no dimensions on it. I has to be in inches per hour. Okay, so our units were in inches per hour, and our acre and our area has to be in acres. So that was 5 acres. Okay, in metric system, our area has to be in square meters, and our rainfall intensity has to be meters per hour. So just be in mind of your units when you're doing these calculations. Okay. All right. Example 9.2. Let's do one in metric. Estimate the peak rate of runoff from a 2 hectare. So A equals 2 hectares. Drainage basin that has a runoff coefficient of 0.4. C equals 0.4. For a rainfall intensity of I equals 75 millimeters per hour. Okay, so again, we need area needs to be in meters. So I'm going to change colors of ink here. So times 10,000 square meters per 1 hectare. So therefore that cancels that out. So that equals 20,000 square meters. Okay, the coefficient is dimensionless, so and our intensity needs to be in meters per hour. So times, so millimeters is on top, times, so 1 meter, therefore equals 1,000 millimeters. The millimeters has to be on the bottom. Okay, that's how dimensional unit dimension changing. So remember, if it's on top, it has to be on the bottom. So we take 75 divided by 1,000, and that equals 0.075 meters per hour. Okay, so now we can calculate our Q. Q equals 0.4 times our rainfall intensity, 0.075 meters per hour times 20,000 square meters, and I will get 600 cubic meters per hour. Okay, but our units need to be in cubic meters per second. Okay, so that means 600 cubic meters per hour times 1 hour equals 3,600 seconds, right? 60. So we divide, the hours cancel out, and that will equal 0.17 cubic meters per second. Or as the book does, it changes into liters per second. There is 1,000 liters per cubic meter. So I multiply that by 1,000, and I'll get 170 liters per second. So that is the answer to a metric conversion. Okay, so just be careful. You got to watch your units here. Okay. 9.3, example 9.3. So as I go through these example problems, go back through these example problems in the book and make sure you can understand them and make sure you can actually do the problem without looking at the problem. Then you have a good understanding of how the problem works and see if you get the right answer. Okay, so let's talk. 9.3 talks about a runoff coefficient. Okay, so on page 219 is we have to calculate a composite runoff coefficient. So basically, what that is, you got to take a percentage of your total area. So if a certain percentage is grass, a certain percentage is asphalt, a certain percentage is woods, it's basically a weighted average of the runoff coefficients to come up with an average one to calculate the flow. So 9.3 goes over that. From an air photo of a 15 hectare watershed, so let me write down what you know. That's how you start these problems. 15 hectares. It is determined that 6.5 hectares is a flat, densely wooded area. Okay. So we have 6 hectares is a densely wooded area. All right. So if I look up on the upper right hand corner on table 9.1, your example in your book uses the lowest value, 0.01. So my C is 0.01. Okay. 6.8 hectares is lawn. So 6 hectares equals lawn. So if I go for lawn, grassed or lawn area, so that's 0.10. Your book uses 0.20. 0.20. Okay. And then and 2.5 acres is paved roadway. Okay. Oops. So this first one here is 6.5, 6 hectares, and then 2.5 hectares is a paved roadway area. So C3, and they use 0.95. Okay, so this equals C1, this equals C2, this equals C3. Let's look at these values on table 9.1. So when you calculate flow, Q equals C times I times A. So the higher the value of the C value, the higher the flow, because if you're multiplying each of these. So basically, this is a judgment, an engineering judgment. Typically what we do is we want to be a little more conservative, pick the fastest flow. So like for a woodland area, we'd get a fast flow of 0.2, a higher flow rate of using 0.20, etc. So that's kind of how these coefficients work. And okay, so now finding, it says compute a composite runoff coefficient for the total watershed. Okay, so C. So if you look at the equation 9.2 on page 219 of your textbook, C equals 1 divided by your total acres, and then I multiply it by the individual acres, 6.5 times 0.01, sorry my text is not too bad, plus 6.0 acres multiplied by the 0.20, that's my C2, that is my lawn area, and add my 2.5 acres for the pavement, and I multiply that times 0.95. Okay, so basically this is one big equation. So what you need to do what's in these parentheses first. Take 6.5 times 0.01 plus 6.0 times 0.20 plus 2.5 times 0.95. Add those up and multiply it by 1 over 15, and then you get a 0.24, and that is your composite coefficient, C composite. And that is the value you would put in your equation Q equals C times I times A. Okay, so that helps determine the flow. Okay, all right. Okay, let's talk about time of concentration, TC. The time it takes a drop of water to flow from the most distant point to the outlet. So if you look at the figure at the right, as I discussed this, there are three components. You have overland flow. So when water hits a lawn, that has to flow to its lowest area. We have shallow concentrated flow, and then we have channel flow. Okay, so when the water hits it, so all that overland flow has to hit into the shallow, into kind of a drainage path. You know, the lowest contours in your yard. You know, there's contours. We get water to flow away from a building. You can call that a shallow concentrated flow, and then that shallow concentrated flow will actually end up into a ditch or a culvert or something, and that's your channel flow. So all those times of concentration, it's kind of a complicated system because it takes time for that water from the hit the lawn to the contours, and then from the contours, time it takes to get to the channel, and then the distance it takes to get it from in the channel to the outlet. So again, let's look at the Fox River, the all the way from Lake Winnebago to Green Bay. So you think about all that watershed going there. So it's a very complicated system. You got all those different kinds of flow flowing into the river, and then eventually your outlet, your discharge outlet, is in the Bay of Green Bay at the mouth of the Fox River. So each of those plays an important part in figuring out time and concentration. So this is actually the hardest part to figure out our flow, because the time it takes to get that max peak flow. So we want to slow that down as best we can, and that's why they have those dams. Because if they didn't open those dams up, our time of concentration would increase, and then we'd get flooding. Okay. So typically, what we can consider time of concentration, or time of concentration, a way we can estimate it, is equal to our storm duration. Okay. So remember, it's a 10-year, 5-year, etc. Okay, a storm duration. So remember, that storm duration is what? And is a certain intensity over a, over a certain amount of time, 20 minutes, 30 minutes, 40 minutes. Okay. So again, going back to intensity, right? Inches per hour. Just reviewing. And then your reoccurrence interval. Okay. Remember, is a particular intensity and duration, how much it'll recur. So these terms will come up again in our next example problems. And then probability is 1 over your reoccurrence interval. Okay. And remember, our rainfall curves are separate for each area. Okay. So example 9.4 from your textbook. And is on page 221. A 62-acre watershed has a composite runoff coefficient C equals 0.25. The flow distance to the beginning of the stream that drains the watershed is 500 feet, and the slope is 7%. The stream is 2,000 feet long and drops 100 feet in elevation by the time it reaches the watershed outlet. Estimate the peak rate of runoff for the 5-year storm and the 100-year storm. All right, a lot of information here. So, okay, we have ink A. Oops, what did I do? Sorry about that. A equals 62 acres. C equals 0.25. Okay. Let's see here. Actually, I'm not really going to have you do this. This is so what I want you to do, it's like you say, it's a complicated system. What this is doing is allowing you to calculate your time of concentration of flow using different graphs and charts. So I'm thinking I'm going to take this out. I don't want you to, let's see, let me look here. Yeah, it kind of goes through using all these different charts and stuff. So actually, I'm going to remove this from the learning plan. So don't worry about this guy because it's kind of beyond the scope of this class here. So I just wanted to explain to you how that time of concentration works. Read through this example problem, you know, briefly so you kind of understand that, again, there's a lot of components, moving parts to make this happen. So I'm going to simplify this. So we're just going to move on. All right, so, okay. Effects of land development. Increase in frequency and severity of flooding. So if we have a wooded area and they chop down all the trees and they place asphalt pavement, we increase frequency and severity of flooding. So woodland, meadowland, farmland turns into paved roads, driveways, parking lots, and buildings. Amount of infiltration decreases, therefore runoff increases. So when we turn farm field into a parking lot, we get more runoff. And then time of concentration decreases. If we have a parking lot, it takes less time for that water to get to the outlet versus a grassy area where the natural soil can absorb that. Okay. So how do we mitigate stormwater? So stormwater, we need to reduce peak runoff rates. So how do we do that? You probably see I just want to talk about silt fencing, and during a construction site, what we don't want is all of that, because a site is typically undeveloped, the grass isn't planted, they don't have the contours, they don't have the stormwater ponds, we get a lot of runoff. So what we like to do is put silt fence in. There's a proper way to put silt fence in. On the upper left hand corner of this picture is it needs to be buried and it needs to be compacted so when the water hits it, it doesn't bulldoze it over like in the bottom picture. Okay, so if you look in the upper right picture, you can see we need to protect any of that sediment running into the river or water body. So that's why you see that, and you'll actually see this fabric in storm outlets. Okay, so it's important that this is inspected, that we're not causing damage. So reduce peak runoff rates. Silt fence will help with that. Reduce severity and frequency of flooding. Reduce soil erosion and stream sedimentation. Protect surface water quality. Groundwater aquifer discharge. So stormwater, these are parts of stormwater mitigation. So there may be times on your job where you have to inspect the silt fence. It's typically a good idea. I know the DNR requires you to submit reports that it's inspected after at least once a week if it doesn't rain. I can't remember. Definitely after a rainstorm. So documentation, documentation, documentation. Okay, so storage basin, retention basins always hold some water, forming a permanent pond or small lake. Okay, so subdivisions, upper right pictures here are retention basins. So basically what it does is it's always holding water for recreational purposes, and then as the water level comes up, it can discharge slowly back into the stream. Detention basins holds the water for a short period of time during and after rainfall. So that you can see in the bottom pictures, okay? So basically the one on the left is a grassy area. that concrete wall there actually stops the flow and it slowly goes through the drain on the bottom of it. And they're typically dry. And then the one on the right, as you can see, it kind of looks like a retention basin. It's just, um, it'll evaporate over time. So as it holds the water temporarily, the sediments sink down, and then as the water goes up, that inlet is near the top of that detention basin, so only clean water exits out of that stormwater pond. And then we have recharge basins, basically allows collected water to percolate into an underlying aquifer. So they made one of these actually at Bay Beach here in Green Bay. They used uh, permeable pavements, a very open graded mix where the stormwater will actually flow through it and be absorbed back into the groundwater. So this eliminates stormwater ponds. So again, it sits in a pond and it's allowed to infiltrate back into the groundwater. So typically that's our lawn. Your lawn in your front of a yard is actually a recharge basin because the water is allowed to soak in and it soaks down. Your sump pump is running, so that means the water is going back into the system. So stormwater detention basin design. So basically, this is a moving animal too. So what we need to do is we need to figure out how big these stormwater basins, what we need to do is how big they need to go so we can fill them up, allow the sediment to settle down to the bottom, and allow clean discharge to come through. Because how do we reduce runoff? How do we reduce that peak flow rate? Well, if we can temporarily store that water, that will slow down that peak runoff rate, and then slowly release it back into the system. However, that water has to be clean. So that's typically the nutshell. How much storage do we have before it starts draining out? Okay. So that's kind of what these graphs are showing you here. So basically, you have a discharge and you have time. So okay. So all right. Basin inflow. Again, I'm sorry. Uh, so it fills up and then it decreases. So basically, so after it rains for a while, we have less storage, and then that water has to exit out of there. Okay. All right. So let's do example 9.8 from the textbook. And that is on page 2. Let's see here. I'm looking for it. All right. A storm causes, I'm on page 233 of your textbook. A storm causes a peak runoff rate of 5 cubic meters per second. All right. So we know Q, peak runoff rate, that's the Q value, equals 5 cubic meters per second in a drainage basin that has a time of concentration of 30 minutes. Time of concentration, 30 minutes. Okay, so remember that time of concentration is either equal to the storm duration, or it's a long calculated process to see how long it takes that water to get to a point. That's basically what time of concentration is. A detention basin with 10,000 cubic meters of volume, so V volume equals 10,000 cubic meters, can be built on a site for a residential land subdivision. Estimate the peak outflow from the basin for this storm. Okay, so we need time and concentration. So if I'm going to look here, I have the formulas in here. or on the upper right hand corner of this slide. So the first thing we have to do is we've got to get time of concentration in seconds, because we have Q equals 5 cubic meters per second and our time of concentration is in minutes. So the units don't match. So I'm going to change ink colors here. So 1 TC equals 30 minutes times 60 seconds per 1 minute, and that equals 1800 seconds. Okay? All right, total rainfall volume is right over here. Total rainfall volume. So step 2, because it's asking us the peak outflow from the basin for the storm. Outflow, going out, peak outflow. So first we got to figure out how much volume is coming in there. So we take 1.5 times 1800 times 5. See, the units match. See, the seconds, everything matches. So we got 13,500 cubic meters of volume of water, rainfall volume. So this equals rainfall volume. Okay? So if you look, we know the problem says a detention basin of 10,000 cubic meters of volume can be built on a site for a residential land subdivision. So if you look here, if we have 13,500 cubic meters of volume, and then our volume of our detention bay is 10,000 cubic meters, we can't store it all. It can't happen. So if you look at that, right, it cannot happen. So from that, we need to figure out a storage, they call it a storage factor. So storage factor equals basin storage volume, which is 10,000, divided by our rainfall volume. So I'm looking at this equation right up there, which equals 13,000. Okay, and that is 0.74. It's a ratio. Okay. So now we need to calculate our flow factor. So that our flow factor is 1 minus storage factor. 1 minus 0.74, which equals 0.26. So basically 26% of that water is flowing out of the detention pond, if you look at it. So now the flow rate, that is a Q term. Okay. So that takes 5 cubic meters per second. So that's our storm volume, our flow rate, our total rate going into that stormwater pond. But remember, it can only hold 74% of it. So how much of it is coming out? Times, so 26% of it's coming out. So my flow rate is going to be 1.3 cubic meters per second. Okay? So remember, how do we slow down, how do we control erosion runoff? We slow down Q, the peak flow, right there. Okay? So that's kind of a neat thing. Hopefully by me explaining that way, it kind of makes sense. So 1.3 cubic meters per second will actually flow out of that stormwater pond. So again, it settles out, and then the exit point is up high where clean water comes out. So sometimes land developments or codes and ordinances only allow a maximum peak flow coming out of a detention pond, a detention pond, and that's controlled by the DNR typically. So sometimes we have to back calculate how big that detention pond has to be to figure out because of a exit rate. Okay, so that's 9.8. 9.9. So I'm still on page 233. Okay, estimate the storage volume needed in a detention basin to reduce peak inflow rate of 150 cubic feet per second to 100 cubic feet per second if the total rainfall volume is 300,000 cubic feet. Okay, estimate the storage volume. All right, so we know we got to go from 150 to 100. So how the problem works, you calculate a flow factor. So we need to go from 150 cubic feet per second down to 100 cubic feet per second. When I divide that, peak outflow rate, peak inflow rate. Okay, I got this backwards. So my outflow rate, I have to design for 100 cubic feet per second, and my inflow coming into that pond is 100 cubic feet per second, and that is 0.67. So I got to reduce that flow rate by 67%. 67% of that. Okay, so that's what I have to do to make that. Okay, so now my storage factor. So if I use this equation and rearrange that, okay, my storage factor to reduce my flow rate from 150 to 100 cubic feet per second, the difference between the two, 0.33. Okay, so remember, it's basically a percentage of the flow, because 100% of the flow, right? So that's what we're doing. We're figuring, okay, how much is flowing out, how much is being stored. So we got to store 33% of that flow. So now applying equation 9.6 is, oops, I'm sorry, I didn't mean to do that. So 0.33 storage factor, right? I'm using this equation right here, equals basin storage volume, that's what they're asking, divided by total rainfall volume. So storage volume divided by total rainfall volume, and they give us 300,000 cubic feet. And basically, we rearrange this equation and we need a storage basin volume of 100,000 cubic feet. So that's the volume. So now, as you know, volume is a three-dimensional term. So we got surface area and we got depth. Okay, so now this is the tricky part. What happens if I have a really small area and I don't have a lot of surface area? So that means my pond has to be deeper. Or vice versa, if I have a lot of surface area, I can make a shallow pond and have a large surface area. Okay, so you kind of see the difference between what's going on there. All right, so that's the answer to that one. So think of it as a percentage of the total flow. That's what this is. All right, 9.10. Referring to the data given in examples 9.4 and 9.6, assume that the local planning board has required that the land developer provide an on-site stormwater storage basin. The peak runoff after development, example 9.6, is to be no greater than it was before development, example 9.4. Assume that the detention basin will have an average water depth of 6.5 feet when filled to capacity. How much area of site in acres will have to be used for the detention basin for a 5-year storm and a 100-year storm? Okay, so this one here goes into a lot of detail. So again, I am going to cancel this one out. So this is all right. So with that, if you want to know more, you can read through the examples. I suggest that you just brief through it and try to understand it. Depends how much time you have and what you want to learn. All right. So now what I want to do is an example problem, uh, not from your textbook, that's related to a problem actually at NWTC. So we'll go through this, and this will be similar to your quiz. NWTC recently developed the Great Lakes Energy Center and artificial wetland detention pond, and an artificial wetland detention pond was required to be constructed. Based upon the drawing, the following design information is known. Okay, so what I'm going to do is, let's see here. So I actually want to show you this, and so basically let's look at this. So this is the artificial wetland pond right here. So this is the Great Lakes Energy Center. So we have buildings here, we have asphalt parking here, and this area is green area, okay? So in here, here's a potential future development right here. So this could change the coefficient, right? Because our coefficient for green areas versus buildings versus runoff are different, okay? So basically, the first step in these design problems is what is the total area that is going to run into that artificial pond? Okay, so that's a determination that has to be made. So you can kind of see the project limits here. They're figuring out all of this water that hits the surface at some time will run into that detention pond, artificial wetland detention pond. Okay, so now time of concentration, right? How long does it take from water if water hits there to get to there, etc. If there's a ditch, a culvert, obviously there's probably a culvert over this drive. So there's a time of concentration that is a complicated mess. But typically what we can do is the storm duration can be our time of concentration. So I just kind of wanted to show you this. This is kind of how you start this, okay? How you start these design problems. So let me go back to this and from current slide. Okay. All right, pre-development area. So that whole area which I showed you is 84,384 square feet. Post-development areas, pavements and roofs are 18,720 square feet. Determine the runoff coefficient prior to the site being developed. Calculate the post-development composite runoff coefficient. Assume a recurrence interval of 100 years and a storm duration of 10 minutes. What is the rainfall intensity in inches per hour? Compute the maximum peak runoff rate for pre-development and post-development. Calculate the total rainfall volume based upon pre-development and post-development flows. Based upon new safety regulations, the depth of the stormwater pond is only allowed to be 1.5 feet deep. How many acres will have to be used for the detention basin if the water depth in the basin is 1.5 feet based upon post-development flows? Okay, so let's work on this example. So problem 1, runoff coefficient. Determine the runoff coefficient prior to the site being developed. Okay, so basically number 1, I am using table, let's see if I can find it, table 9.1 on page 219. Okay, let's see what color I got here. So problem 1. So pre-development is a green area. So it is a grassland or lawns. So as you looked at I didn't show you the legend, but the legend, you got to look at kind of what material that is, grassland or lawns. So that is from 0.10 to 0.25. What I like to do, because remember I said you're going to get a more of a flow of 0.25 versus 0.10 using the coefficient. Okay, so what I like to do, I take the average. So when I take the average, I get 0.175. That's the answer to that's pre-development runoff coefficient. Okay, so that's problem 1. Problem 2, calculate the post-development composite runoff coefficient. So pre-development area. So that's our total area, correct? So if I go to equation 9-2 on page 219, it's 1 divided by my total area of 84,384 square feet. Okay. My roofs and pavements are 18,720 square feet. So my net, how do I figure out my net green area? I basically take 84,384 square feet and subtract it from 18,720 square feet, and that's how I get my net green areas. Okay, so I know my green area is 0.175. My roofs and pavement, so if I look at page 219, table 9.1, pavements and roofs 0.70 to 0.95, I get an average of 0.825. Okay, so I multiply this by 0.175, that's my green area average coefficient, times 65,664 square feet. Okay, where did this number come from? I took my roof and pavement area given in the problem. It's basically this number minus this number. That minus that will give me my net green areas. Okay. Plus, my average coefficient for pavements and roofs is 0.825, and I multiply that by my area, which is 18,720 square feet. And basically what I get is my composite runoff coefficient is 0.319. So that's the C in the term. Okay. All right, so 1 and 2 answered. Let's go to number 3. Assuming a reoccurrence interval of 100 years, or storm period, and a storm duration of 10 minutes, what is the rainfall intensity in inches per hour? All right, so we need to go, to our rainfall curves somewhere. And I don't have it on this PowerPoint. Remember these here, but I want you to use the Green Bay curves. And I'll have to make sure. Let's see here. That is attached. I'll make sure that is attached in Blackboard So number you can use Green Bay curve. So I'm going to go what do I have? Let's see, let me read the problem. Storm duration of 10 minutes and a 100-year storm. I find my intensity per hour, and based on that curve, sorry, I don't have that in front of me. For some reason, uh-oh. Why are you contacting server for information? It is recording, but my screen has locked up, so I'm going to pause it for a second here. Okay, we're back at it here. Oh, okay. Sorry about that. All right, so we're back at our problem here. So based on that, I get 9 inches per hour. Regroup here. Okay, problem number 4. Compute the maximum peak runoff rate for pre-development and post-development. Okay. All right, so Q equals C times I times area. Okay, so pre-development, that equals, so C, so pre-development is 0.175 times intensity, 9 inches per hour, times my acres. Okay, so remember, this has to be in acres. So pre-development area is 84,384 square feet divided by 43,560 square feet. And then that is 1.94 acres. So watch your units. And I get 3.06 cubic feet per second. Okay. And then post, I get 0.319 times 9 inches per hour times 1.94 acres again. Remember, you make sure the units are right. And I get 5.57 cubic feet per second. Okay, so that's how you calculate that. All right, so that was 4. Compute the maximum peak runoff for pre-development and post-development. 5. Calculate the total rainfall volume based upon pre-development and post-development flows. Okay, so that is this equation right there. So pre equals 1.5 times time of concentration. We're going to assume 10 minutes because when calculating number 3, I said a duration of 10 minutes. And that is a really general, basic assumption that my time of concentration can equal my storm duration times 10 minutes, but that has to be in seconds, times 600 seconds, okay, times my total area. So 84, let's see here, of Q max. So times, this is the pre-development, times 3.06. So I need a volume of 2,754 cubic foot. Okay, now in post-development, okay, I get 1.5 times 600 seconds times my flow Q at post is 5.57 cubic feet, and I get 5,013 cubic feet. Okay. By just adding that, if you look at the reason why you want to look at pre and post, so by looking at that, we almost doubled our volume of rain by just adding that building in the asphalt pavement there. So that's quite a big difference there. So this is what we do. You determine the pre and the post. So because they want to limit those post flows. Okay. All right. Based upon new safety regulations, the depth of stormwater pond is only allowed to be 1.5 feet. How many acres will have to be used for the detention basin if the water depth in the base is 1.5 feet? So basically it's full based upon post-development flows. So now I'm assuming storage, that I want 100%, this problem I want 100% storage. Okay, so I'm assuming nothing is flowing out at the time. Okay, now that can be, it becomes a more complicated problem when I have when I have flows coming out. I'm assuming at this time and moment as I cannot assume that any flow is coming out. So it's all going into that detention basin. Okay, so I'll use a different color here. So if we know we have, so this is problem 6. If we know I have 5,013 cubic feet, right, divided by, okay, that's the depth. I'm going to get my area, right? And then I get 3,342 square feet. Now I convert that into acres. I know 1 acre equals 43,560 square feet. I divide that out. I get 0.076 acres. So that's how big my stormwater pond has to be, assuming I can hold 1.5 feet. So what if I don't have 0.076 acres? What if I have less than that? So that means I have to make my stormwater pond. So there's all these calculations. Okay, so that is a really basic stormwater pond flow. So that is it for this presentation. So thank you and have a great day.